Hello, hello, hello. Let's get into the kryptonite of this course, for me anyway, and it takes me down a rabbit hole, which is probably not worth troubling yourself with too much because I bet you can pass this course and get a great grade without thinking about the math. But for me, it's very difficult. So let's get into it. When we're looking at probabilities, never start studying probability with this kind of thing. That's what I've learned first. The math is always second to drawing it out. So let's go and draw out Bayes' rule, and then you'll see how simple and easy it is. Before we go and draw it, this is conditional probabilities we're looking at. In other words, if this variable is not independent of that variable. In other words, that variable changes when that happens. So for example, if you're drawing balls out of a box and you draw the ball out and you don't put it in, then you draw another ball and you don't put it in, then you draw another ball, then you don't put it in. That's Bayes' rule. It's that simple. Okay, so let me show you how it looks as a drawing, a probability tree. Oh, okay. Let's read it first. The probability of A given B is the probability of B given A multiplied by the probability of A divided by the probability of B given A, the same number again, times the probability of A, the same number again, times the probability of B given the complement of A times the probability of the complement of A. Okay. So if you were looking at that, you could take those out because they're the same, and you would be left with 1 over the probability of B given the complement of A times the probability of the complement of A. So let's go and look at that formula in Excel as a probability tree. Right. So if we were looking at Marie, the probability of Marie winning and getting the trophy, there's a 50% chance that she wins and a 50% chance that she loses. Okay, so the complement of this stream of probability A is the complement of A, okay, 1 minus A, because it's always going to add up to 1. All of the possible outcomes always add up to 1, right? So she wins. Then she's got a 60% chance of getting the trophy and a 40% chance of not getting the trophy. The complement of 0.6 here is going to be 0.4. Okay, it's either A or B. She's either going to get the trophy or not get the trophy. To calculate whether she gets the trophy or not, you multiply this line with this event with this event. Okay, this occurrence with this occurrence, and you get that answer. If she won, didn't get the trophy, that's the odds of that. Multiply that by that. If she loses, obviously she's got no chance of getting the trophy. And if she loses, she's got 100% chance of not getting the trophy times that line, 0.5 is 0.5. And if you add all of these possible outcomes up, you get 1. That's what Bayes' theorem puts into math, all right? Here's another probability tree, this time with 3. And this time it's about what happens if the first outcome changes the second outcome, which changes the third outcome, which changes the fourth outcome. You can draw it out in a long line of these kinds of things. Okay? So, for example, if you've got 3 balls, unfortunately my colors don't match. Okay, you've got nine balls in the box. 9 balls in the box. There's 3 colors. All right. You take out the red ball. You had a third of a chance of getting a red ball because there were 3 red balls, 3 yellow balls, and 3 blue balls in the box. You take out a red ball. You've got a third of a chance of getting that. Here it is drawn out for you. Okay. Now, the second time you draw, what's the odds of getting a red ball again? Now, you've taken out 1, so that means there's 2 balls, and there's only 8 balls in the box. So that's 2 out of 8, right? Then The yellow ball, there's still 3 yellow balls in that box, so you've got a 3 out of 8 chance of a yellow ball. And blue balls, there's 3 blue balls in the box, so it's 3 out of 8. And this adds up to 1. This adds up to 1. Okay. And you could do it again with out of 7, and then again out of 6, and then again out of 5, all the way down to there being 1 ball in the box. So that probability tree shows you how you can do some math with a diagram. And instead of having this complicated math that makes your head spin, you can use a diagram. Okay, now we're going to jump over to the next challenge here is binomial distributions. Okay, so before we do that, we're going to go a little bit ahead to a normal distribution and then come back to a binomial distribution. So we're first going to look at, so where's this in the book? Okay, so it's on page 42 of the book. So we're going to jump from this page, Bayes' theorem, page 37, to page 42, and then scroll back again. Okay, so page 42, before we do anything else, we just want to look at binomial distributions can be skewed or straight. Okay, there's a little number here. Here we go. All right. So if we look at probabilities, if you threw a coin 3 times, right? And you repeated that experiment 8 times, you can work out the probability of throwing no heads, the probability of throwing 1 head, the probability of throwing 2 heads, and the probability of throwing 3 heads in that 8 times. And here, you'll see that it's less likely that you'll throw 1 head, that's common sense, and more likely that you'll throw 1 or 2 heads, and less likely again that you'll throw 3 heads. And if you look at these numbers, you can see that they are symmetrical. In other words, the odds of throwing 3 heads is the same as throwing 0 heads. And here, the odds of throwing 2 heads or 1 head are the same. Okay, that's all we need to know there. Now let's look at that drawn out. And I'm going to jump over to Alison. I recommend this course. Oh, wrong thing. Hang on. Yeah, here we go. I'm going to just maximize this. And we're going to have a look at it. All right, so this is a normal distribution around the mean. Okay, in other words, the probability of throwing the average is symmetrical around the center. Okay, here it's a different example, but it's the same principle. It's a normal distribution of the mean. It's symmetrical. It's equally likely that you're going to throw something like 0 heads as it is to throw 3 heads. Equally likely to throw 1 head as it is to throw 2 heads. Okay? Now, say your coin had been specially made by a gambler who specialized in gambling on coin tosses. And this gambler wants to win when people throw a head. They're going to bend that coin so it doesn't always land on a tail somehow. This is a positive skew. It's more likely to be above 10 kilograms, more likely to be above the average. And if it looks like this, it's skewed to the left. So positive is to the left. So the hump is to the left. That's what I find confusing. So positive is to the left, because I normally think of positive to the right, right? But here positive is to the left, and it's a higher chance of being a higher number because this area is smaller than this area. Here, a negative is to the right. It's got a greater chance of being smaller than the central number because this area is bigger than that area. Okay. So that's comparing distributions. There's a normal distribution and there are skewed distributions. Now this comes in handy with, because you're throwing something multiple times, you're throwing those coins multiple times, there's multiple experiments, okay, or multiple samples. And say what we're doing here is we're saying what we expect is that it's going to be symmetrical around the average. That would be a random set of experiments where it will over time become more and more and more symmetrical around the average. The more often you throw, the more closer you're going to get to the average. Here, there's something going on. It's not symmetrical. In other words, it's not random. There's something else influencing this outcome. There's other variables. Another word for this shape in politics is called a Russian tail, and I'll show you why. Let's see. Here we go. The Russian tail. This is interesting. Okay, so in a fair election, I can't get rid of this thing on the right, sorry. In a fair election, you'll get a normal distribution around the mean. Each of these is a little voting district in America, in Clark County, okay? And this is what happened on election day. You can see, okay, these guys are high and these guys are low, but overall, it's symmetrical. Can you see? Each little county balances out to a mean. All right, the normal vote distribution. Here we have a Russian tail. This was the early voting counting for Trump. Can you see that this is skewed to the right, which means that it is a negative. There's more on this side than on this side. So these voting stations, once a certain percentage of people had voted, the numbers changed significantly. So as the experiment, as the samples continued to be drawn, the numbers shifted. And this is called a Russian tail because this statistical pattern was seen in the 2020 vote in Russia as to whether Putin could have multiple terms. So that is not randomized. There's something going on. So that's interesting. Okay. Right, so we've looked at that. Now let's go back to Alison, and we're going to actually watch this whole video because it's going to explain binomials to us and show us how that very complicated formula that we have on page 42 is reached. Okay, so let's just have a look at where we are in the book quickly. Okay, so there's this long, complicated explanation over here, which makes our head spin. This is why it's so important. Okay, and it's counterintuitive, so it's exciting and it's worth learning and it's worth being able to use. It's like so powerful. It's so powerful. It's used all the time. Here's our formula. Now, when you look at this, your head is going to go, poof, I cannot understand this. And even though I've come back to this so many times, my head still spins. So let me show you how to understand it so easily. We're going to watch a video. It's about 9 minutes long. And I recommend going and doing this course. It's amazing. Okay, binomial distribution. Here we go. Okay, so pause it as you go along, write it out as you go along, and it will all make sense. It's actually 11 minutes. Let's go. Oh, sorry. 1 moment. Damn.
First of these is the binomial distribution. And this is when you do an experiment which has got two possible outcomes. That's the bi in binomial. and you repeat the experiment many times. You might toss a coin 50 times, heads or tails. You might toss a drawing pin 100 times, pin up or pin on the surface, and so on. Whenever there's two possible outcomes, each time you do the experiment, the probability of a success is the same. And we use the word success or fail, although we might not really think of it as having any particular value. So we might say a head or a tail, or if I roll a die, I might get a 6 or not a 6. Two outcomes, so it's binomial, and the probabilities are the same each time we roll that die. They do not depend on what happened last time. There are more complicated situations called Markov processes, where what happens next time does depend on what happened before. If we think about weather, is it sunny or rainy? That depends on what happened yesterday and then on the day before. But binomial, the probabilities are the same each time.
So, for example, that 9 balls problem, that would be a Markov process, slightly different math. We're now looking at each one is independent. So as you go along the probability tree, you're not having to -1 on both sides. You can just continue with the same odds, okay? You can draw a probability tree and it will be heads, 1, 1, 1, 0.5, 0.5, 0.5, 0.5, 0.5. Okay, let's go.
We do a fixed number of experiments. So let's, for example, toss a drawing pin 3 times. And let's suppose that the probability of getting a pin up is 1/4. That's that scenario. What are the probabilities of the different possible sets of outcomes? Well, we can analyze this with a tree diagram. The first toss of the drawing pin, we can have up or down, and that's 1/4, and that's 3/4. And we can have the second throw. Again, it's 1/4, 3/4, 1/4, and 3/4. That's the second throw. And I can have the third, or the third toss of the pin. And again, whatever had happened before, I can still get pin up or pin down. And again, it's going to be the same sequence of probabilities. The pin does not remember what it did before. We should always remember that these inanimate objects, if you toss a coin 20 times, if it's a fair coin, even if you've got 20 heads in a row, it's still 50-50 next time. Coins do not remember. Drawing pins do not remember. Now we know how to work out the probabilities of the various patterns. The chance of getting 3 ups is 1/4 times 1/4 times 1/4. Which is 1 out of 64. The chance of 2 ups and a down is 1/4 times 1/4 times 3/4, which is 3/64, and so on. And there are 8 possible sequences. But what we're going to be interested in is how many different ways can, for example, 2 ups and 1 down occur. What is the total probability of getting up twice when I do the experiment 3 times? This was one way of getting a UUD. Another way of getting 2 U's is this sequence. 3/4 times 1/4 times 1/4, which is 3/64. That was a down followed by 2 U's. And in here, I missed it out. There's another one with 2 ups. If you get up, down, and then up, and that's 1/4 times 3/4, 3/64. And those are the 3 different ways in which we can get 2 ups and 1 down in 3 tosses of the drawing pin. And what we want to do is find a quick way of doing this calculation. This tells us, of course, that the probability of getting 2 ups is 3/64 plus 3/64 plus 3/64, because with tree diagrams we add alternative trails, so we get a total of 9/64. Now, the idea of the binomial distribution is to try and put this into a simple form whereby we can work this out immediately without having to draw tree diagrams or do lots of repetitive calculations. Let's try and figure out what's happened and how we can generalize that. Let's now look at a case where we have an experiment. So we repeat an experiment n times, and the probability of a success equals p. So in this case, that was a quarter, and we did it 3 times. What's going to happen generally? Well, we can imagine what the tree diagram would look like. So the probability of x successes, how can I get x successes? Well, the successes might be the first couple. So when I was chasing ups, I could have my 2 ups and then the fail. And the chance of that is the chance of the first success, which is p, times p. And I will keep doing this, x times p times p times p. I want a success and another success and another success. I keep doing that, x times. And the remaining experiments, in this case, there was 1 left. We wanted 2 ups, so there was 1 down. That came at the end with its probability, and that probability is 1 minus the original. So what I now need is the chance of getting a fail and another fail. And if there are n experiments altogether, in this case 3, if there were 2 successes, it was 3 minus 2 fails, which is 1. In this case, I will want n minus x fails. That's the probability of one particular trail through the tree diagram. But what we now have to do is see how many different trails would all give the same.
Okay, so this is worth slowing down and just absorbing, right? I recommend drawing it out. So the x is the number of successes in n number of trials, okay? So it's that success, is that a plus or a times? Times that success times that success. And then the number of fails is n minus x. So if you're doing 3 experiments and you got 1 success, then it's n minus x is 2, okay? So it's just taking it off the total number of experiments. And that'll be 1 minus success times 1 minus success times 1 minus success. Okay.
Same final outcome, in this case 2 ups. So we have to multiply this by the number of different ways that you can get x successes in n experiments. And for the moment, I'll just put a formula here, or a label. It's called n choose x. And that's called a binomial.
N choose x, okay. These you get out of tables. So we're going to get used to that being plugged in as a formula that you get out of a table. And I think those tables are in one of the appendices. I think it's in Appendix 9. Let's have a look. Appendix D, wasn't it? No. It will be in one of the appendices, most likely. Must be somewhere in here. No? Okay, never mind. Let's keep going. I'll look for it.
Coefficient. And we work this out. And sometimes it's written as a bracket. Looks a bit like a vector, nx. And this formula involves factorial numbers. n factorial over x factorial times n minus x factorial. Now, factorial n is that number.
Okay, so that n choose x, that is the formula, how they got that, which you can work out yourself with the factorials, or you can look up in a table. So let's just quickly go and look at the book, hopefully without getting lost and wasting our time. There we go. That's our factorial, n choose x, okay? So that you pull out of a table. You don't need to calculate it. That's n choose x. That's the formula for n choose x. So here, the binomial formula is the probability of getting x number of successes is the number of experiments over x factorial times n minus x, okay, the probability of failure factorial, okay, which we get as n choose x, and we get it out of a table. So that part will be done for us, and we don't need to think about it beyond knowing that this is that binomial thing, okay? Let's go back. Where were we? Haha. No, I haven't stopped learning. It's a little bit hasty, that auto thing. This is the course I recommend everyone does. It's free and it's on Allison. I love it, love it, love it.
Number times the next one down, times the next one down to 1. So that tells you how many different branches in the tree diagram would all represent the same final outcome, 2 ups out of 3. We're not bothered about the order where these successes occur. We just want to get the right number of successes. So let's see how this works out in our case. Going back here, we'd have p to the power x. Well, let's first of all summarize this. P to the x, 1 minus p to the n minus x times n choose x. That's the binomial formula for working out the probability of getting x successes in n experiments. So in our case, p was a quarter, and we wanted 2 successes out of 3. 1 minus p, 1 minus a quarter is 3/4. And we wanted 3 minus 2, which is 1 fail. And then we wanted 3 C2. Often we say 3 choose 2. And that's 3 factorial over 2 factorial. And then 3 minus 2 is 1 factorial. So a quarter squared is a 16th. 3/4 to the 1 is 3/4. And then 3 factorial is 3 times 2 times 1, which is 6. 2 factorial is 2 times 1, and 1 factorial is 1. And so we can see that this is going to give us 3. It's the 3 different ways in which we could get this particular outcome. So if I multiply this all together, I get back to 9/64 as before. So that's the formula for the binomial distribution.
Yeah, that's paused. Okay, right. So that's binomials. All right. So that you can get, you can also type that into the Google search engine as give me the number for n choose x of the 2. Okay, number of trials and number of successes. Easy. So if you're being asked, like for example, here, he's giving an example, or he or she is giving an example of calculating the number of successes being 1 in 10 trials. N would be 10 and x is 1. So if we go to Google, okay, and we say n is 1, x is n is 10. So we'll say 10 choose 1, okay, equals 10. There you go. That's all you have to do to get that number. 10 choose 1, okay? 10, choose 1. So 10, choose 1, that's 10. Okay. And you can also see, if you look at this, he simplified from that formula that we were looking at a moment ago for factorial to 10 factorial over 9 factorial, which is 10 over 1. So it's 10. And we looked it up with Google. So then all you have to do is multiply this part, okay? And that part is the probability to the power of x. Okay, so P is the success, right? Success to the power of x, x is 1, times 1 minus the success. The probability of x is n choose x times, which is 10, times P, success to the power of x, times 1 minus success to the power of n minus x. Okay, times 0.5 times 0.01953 is a very small number. 0.5 to the power of 9. There you go. So here it's times 5 to the power of 1, because x is 1. 0.5 is the probability of success, because we're tossing a coin. 1 minus 0.5 to the power of 10 minus 1. Probability, so that would be n minus x. Okay, so that becomes 5 times 0.5 to the power of 9. Out comes the calculator, and Bob's your uncle. You've got your answer. Okay. We don't have to calculate the full number when we're dividing. So this is telling us that 10 choose 1 factorial is 10. Okay. And that you can look up on the internet. You don't actually need a table. All right. So we are going to be doing this for a tiny percentage of your outcome. So don't kill yourself trying to understand this like me. Just move on and finish the course and get on with your life is what I recommend. I never take my own advice though.